Hello and welcome to Vodcast 16.5. In this vodcast, I will discuss the end stages of high-mass stars, specifically neutron stars and black holes. In the previous vodcast, we considered low-mass and mid-mass stars, and those stars died quiet, graceful deaths, forming white dwarfs. But massive stars will die a little bit differently. When we reference massive stars, we're typically talking about stars that are 8 times the size of our Sun, or more. These massive stars are born from a very, very large nebula. As that nebula contracts and heats up, a very large protostar will be formed. Over time, that protostar will become a main sequence star. And keep in mind that massive stars will be blue-colored as main sequence stars. These massive main sequence stars will consume their fuel at very rapid rates, and their lifetimes will only be in the millions of years. In the later stages of life for massive stars, they will form red supergiants. And a red supergiant is similar to a red giant, just much, much larger. Now, when these massive stars ultimately terminate, there will be a massive explosion known as a supernova. During a supernova, the star will become millions of times brighter than it was in its pre-nova stage. The ultimate end stage for massive stars is either a neutron star or a black hole. And in this vodcast, I will go into further detail about both fates. Before going any further, I'd like to elaborate on supernova explosions. A supernova is the most explosive event in our universe, and supernovas will only occur in high-mass stars that are much larger than our Sun. What's really interesting about supernovas is that the heaviest elements in the universe are produced during these supernova explosions. You can't produce heavy elements like gold, silver, lead, and tin without enormous amounts of energy. Supernovas are the natural source for that huge amount of energy needed to produce these really heavy elements. So if you have a gold or a silver ring, you're wearing some of the remnants of a supernova explosion. If a supernova explosion occurred in a nearby star in our own galaxy, it would shine much brighter than our Sun for many weeks. It's important to note that at the very centers of these explosions is either a neutron star or a black hole. And at this point, we're going to shift our attention to those two fascinating objects. Before overviewing neutron stars, I'd like to discuss a very surprising realization about white dwarfs. Scientists have found that the smallest white dwarfs are the most massive white dwarfs. This is due to the fact that when low-mass and mid-mass stars collapse, the largest stars have more of a gravitational pull, and due to that gravity, they can get squeezed into a smaller, tighter space. This conclusion led scientists to speculate that the most massive stars may be able to produce the smallest, densest stellar remnants. And sure enough, one of these types of stars is a neutron star. Neutron stars form from massive stars, or more specifically, stars that have an initial mass greater than or equal to 8 times the size of our Sun. And they're called neutron stars because the gravitational force will literally collapse atoms. Inside of a neutron star, electrons and protons are squished together under incredible gravitational forces. And when you squeeze a positively charged proton and a negatively charged electron together under immense gravity, you end up forming an electrically neutral neutron. A neutron star will have a very, very small size despite its huge mass. In fact, a typical neutron star could be fit into an area roughly the size of Chicago. Taking the size and characteristics of neutron stars just a little bit further, I'd like to show you this picture of a neutron star being placed next to Manhattan. If you can imagine taking a star much bigger than our own Sun and squeezing it down to the size of a fairly large city, it should make sense to you that that is going to be an extremely dense object. Keep in mind that our Sun, as it currently exists, could fit about 1 million planet Earths inside of it. So now take a star much bigger than our Sun and squeeze it down to the size of a city, well, you have a very dense object. In fact, if you were to take a teaspoon and scoop out a pea-sized sample of neutron star dust, it would weigh 100 million tons. Neutron stars also have extremely strong magnetic fields, and they rotate rapidly. The first neutron star was discovered in the 1970s, and pulsars are neutron stars that emit pulsating radio waves. If you ever have the chance to listen to the clicks of a pulsar, do so, because this will give you an idea of just how fast neutron stars rotate. What's interesting is the first neutron star that was discovered was found in the Crab Nebula, and that neutron star is a remnant of the supernova that occurred in 1054 AD, and it lit up Earth's sky with a brightness greater than our own sun for multiple weeks. The final consideration in this vodcast is one of the most awe-inspiring occurrences in nature, and that's the black hole. Black holes are objects from which light cannot escape because of the immense gravitational pull at their surface. Black holes are also produced during supernova events, but black holes will only form when the most massive stars in our universe die. In fact, black holes will form from stars that have initial main sequence masses greater than 25. What that basically means is black holes form from stars that are 25 times bigger than our sun. Black holes are more dense than neutron stars. And to imagine just how dense black holes are, imagine taking a star much, much bigger than our own sun and squeezing it down to the volume of the tip of a pencil. Now keep in mind that black holes are not empty space. They are very, very dense objects. In fact, they're so dense that their gravity will pull nearby material irresistibly in towards them. And because their gravity is so strong, even light can't escape their pull. What that basically means is these objects do not emit light, hence why they're called black holes. Now you may be wondering, if they don't emit light, how can we see them, and how do we know they exist? Well, as black holes pull material in towards them to feed on, that material gets accelerated to fractions of light speed. And when matter approaches those kinds of speeds, it emits X-rays. Black holes are one of the only naturally occurring objects that's capable of producing X-ray radiation. And scientists have instruments that can detect X-rays, and sure enough we find X-rays coming from areas that are candidates to have black holes. And the chicken and the egg debate often comes up, because we find black holes at the center of almost every single galaxy we look at. So the question is, was the black hole originally there and the galaxy formed around it? Or did the galaxy form first and then the black hole form later? That, among with many other questions regarding black holes, are being investigated by scientists. And it's important to note that the source of those X-rays is the accretion disk. And the accretion disk is where gases spiral around a void while emitting a steady stream of X-rays, just before they enter the black hole. Okay, that's the conclusion of this video podcast. If you get a chance, check out some of the additional videos I've included on our Moodle page regarding black holes. In our final 2 vodcasts for Chapter 16, I will overview galaxies, galactic clusters, and the end fate of our universe.